All right, so for the past few weeks, we've been dealing with forced convection, air being blown across flat plates. We'll start off with flat plates. In the laminar case, got an actual analytical result for that. And then turbulent case for flat plates, other geometries similar to spheres, had a bunch of empirical relationships for all of those. So we had, basically now we've done forced convection over every shape we're going to do. Today, we're going to deal with free convection. So there's no actual source of air being blown across any of these. There's no fan or anything, no pump pushing the fluid across this. This is all just natural buoyancy-driven effects. So again, I heat up a plate. That plate heats up the air around it, and then that air around it moves because of the density differences. So that is the topic for today, basically chapter 9. So as I said, previous discussion only dealt with forced convection. There was wind or something going on. Natural or free convection, topic of today, due to buoyancy effects from the changing density resulting from the heating process. So you can kind of see this. There's some decent videos. If you look at air over an asphalt road on a really hot day, that black road is going to heat up quite a bit. And then if you look at it, you can actually see little kind of what look like streams of air kind of going up in this kind of wavy form. Same thing happens in ice and water. Sometimes you can see in that case, though, the water actually goes down because it's a cooling thing as opposed to heating. And so just like forced convection, we'll start with the easiest case. Easiest case is a vertical plate. So essentially what we have is a very similar setup to what we did for the forced convection of the horizontal plate, just everything rotated by 90 degrees, because again, as I heat up, my air is going to move upwards. And so I'm going to create this boundary layer over the plate. Same sort of conditions. I have a no slip condition at the wall. So my velocity is 0 at the wall. However, the difference here is that the velocity at the outer edge of the boundary layer is also 0, because here my kind of free stream velocity, if you want to call it that, is technically 0. So the only velocity I have is within the boundary layer. So I have a different velocity profile inside the boundary layer than I did for the forced case. And initially, I have a laminar boundary layer, could go turbulent at some point at some value, kind of similar to what we had for the forced convection case. We had this transition at a Reynolds number of 5 to 1,000. This case will be different. There really is no Reynolds number here because, again, my free stream velocity is 0. So technically, the Reynolds number is 0. So there's another condition that we're going to see that controls whether this boundary layer is laminar or turbulent. We can start off with the easiest case, which is the laminar case. Just like the forced case, this is the only one we're actually going to have a mathematical result for. Every other case other than this, we'll see empirical results. So we start with pretty much the same procedure we did before. Again, just rotate my coordinate system, x and y, so that it looks exactly the same as the previous case for the forced convection with the horizontal plate. End up with the same overall governing equation. The only difference now is that I have 2 extra terms. So these 2 terms didn't exist in the previous one because I didn't really have any sort of pressure gradient. I also didn't have any gravity effects when I did this for the forced convection over the horizontal plate, so it's horizontal. So now, because I'm vertical, I need to add these 2 guys. My pressure gradient in the x direction, that comes from the hydrostatic pressure of the fluid. And so here I have a rho infinity. So essentially the density of the fluid out here that hasn't been changed compared to this guy. This density is the fluid inside my boundary layer. So that is the one that is the stuff that does change and is the reason for the motion. So plugging that in, I get this term G, rho infinity minus rho, and that's basically my buoyancy driven term. So this is what's actually causing the motion, is that density difference between the free stream and the density inside the boundary layer. So last time, forced convection, this was just 0, but now I have this extra term in there. The density difference, generally express that in terms of a volume coefficient of expansion, beta. So beta is defined to be 1 over the volume, change in volume over change in temperature at a constant pressure. And kind of we can approximate that as change in volume, V minus V infinity, change in temperature, T minus T infinity. And then we can use ideal gas law to convert these guys into density. So instead of volume, I want density. Sorry, not ideal gas law, it's just actually definition of density, mass over volume. Mass is constant, so volume is essentially 1 over density. Then plugging that in to the previous equation, in very similar term. Right-hand side, G rho beta T infinity minus T. So again, this is my driving term. The viscous term is still there as well. That's my momentum equation, essentially. We can also make an energy equation for free convection. This guy is going to be exactly the same as what we had for forced convection at low velocity. Again, in the forced convection case, low velocity, the laminar case. I'm expecting these velocities to be low as well, especially at the beginning. So I have the same energy balance equation. So again, same result that we had from a few weeks ago. Then making some approximations, fluids incompressible. Also have the boundary conditions, again, velocity being 0 at the wall and at the edge of the boundary layer. I can find this temperature distribution, T minus T infinity over T wall minus T infinity is 1 minus y over delta squared. So again, delta is my boundary layer thickness, just like before. And velocity profile, so what this velocity actually is at any point, u over ux is y over delta 1 minus delta whole thing squared. So again, delta is my familiar boundary layer thickness, and then ux is some characteristic boundary layer velocity. So in the force case, I had u infinity. That was my characteristic velocity. But again, in this case, u infinity is 0. I don't have it. So I just have to have some sort of ux, some unknown characteristic velocity inside the boundary layer. Putting these guys back into my original differential equation and doing a lot more math that I'm going to spare you the details on gives me following equation for my Nusselt number. So Nusselt number based on my location x is h times x over k. Again, same standard definition of Nusselt number. This guy is equal to the Grashof number over 4, all to the 1/4 power. And then g is a function, a defined function. So this function down here is a function of only the Prandtl number. So again, GR is called the Grashof number. It's another one of these dimensionless numbers. It's equal to G, so gravity, times beta, this volume expansion coefficient, temperature difference, T wall minus T infinity, X, so again, where I am on the plate from the leading edge, so X equals 0 down here, and then moving upwards is my X direction. And then kinematic viscosity, mu, squared on the bottom. And as I said, this function G is just this function here, function of only the Prandtl number, so 0.75. Prandtl number is 1/2 power. On the bottom, 0.609 plus 1.221 Prandtl number to the half, plus 1.238 times Prandtl number, whole thing to the 1/4 power. So that's just some number based on the Prandtl number that goes there. So this G is just some function not related to this G, which is gravity. As usual, the heat transfer coefficient, Q at the wall, I can take the energy balance between the energy being conducted through the wall and the energy being convected away from this free convection. So minus Ka dt dy at the wall is Ha T wall minus T infinity. Again, I'm going to do this, going to find H using the Nusselt number. But again, like I did a few weeks ago for the forced convection case, that Nusselt number equation we had on the previous slide was for the local value, depending on where I am, the X location. And so I don't really want the X location, I want the average over the whole thing, again, like we did before. For the force case, that was just twice the value at the end. For this free convection case, it's actually 4/3, 1.33 times the H value at the end. So the equation I like to use for Nusselt number has this additional 4/3 in it, times Nusselt number at the end. So Grashof number, again, at the end at X equals L over 4 to the 1/4 power, and times that same function G for the Prandtl number. So this Grashof number, what it does is compares the buoyancy forces to the viscous forces. So I had the buoyancy, the beta term on top with G. So G times beta is kind of my buoyancy forces. On the bottom, I had kinematic viscosity squared. So those are my viscous forces. The Grashof number tells me that relationship. Usually, the way this is done is not necessarily with the Grashof number, but with something called the Rayleigh number. Rayleigh number is just the Grashof number times the Prandtl number. And this Rayleigh number is what's going to determine whether the flow is laminar or turbulent. So it kind of plays the same role as the Reynolds number did for forced convection. Critical value in this case for the Rayleigh number is 10 to the 9th, basically a billion. If the Rayleigh number is less than a billion, we have laminar flow. If it's greater than a billion, we have turbulent flow for this free convection case on a vertical plate. So everything I did before assumed no turbulence, and so assumed I had a Rayleigh number less than 10 to the 9th. So that's how I deal with laminar free convection on a vertical plate. Any other scenario, so turbulent case, as well as other arrangements. So we have horizontal plates, we can have spheres, we can have cylinders. Those are generally all done empirically, and so we'll see those relationships on the next few slides. So usually the empirical relationships look something like very similar form to what we had for some of the free convection cases. In those cases, I had some constant times Reynolds number to some power n. Here again, it's not the Reynolds number that's important, it's the Rayleigh number. So same sort of form of the equation. My Nusselt number is some constant c, Rayleigh number to some power n, and those values of c and n are going to depend on the exact scenario, whether it's laminar, whether it's turbulent, what the value of the Rayleigh number is, what the geometry is. So very similar to some of the cases we saw for the force case. And just like the force case, all these properties, so the Grashof number, Rayleigh number, Prandtl number, everything to do with the fluid itself should be evaluated at the film temperature, so the average of the wall temperature and the temperature T infinity. Characteristic dimensions, so a lot of these have an L in it, so again, based on the length of the plate L in the previous case, if I'm dealing with a cylinder or sphere, that L gets replaced with diameter. So this is the diameter that I want for all these Rayleigh number calculations. So the vertical plate case, again, I can have an empirical relationship for the Nusselt number, HL over K, that looks like some constant times Rayleigh number to the power n. There's actually an empirical relationship for laminar flow. So this is kind of an alternative to use instead of the one we saw before. You can use C being 0.59, Rayleigh number n being 1/4. That's going to give you very similar numbers to the equation we had before, the actual analytical mathematical equation we derived before. So in the laminar case, that should be very, very similar. For the turbulent case, above 10 to the 9th, C is 0.1, N is 1/3. Again, that gives you the value of the Nusselt number. From that, you can find H. From that, you can find the heat transfer. So again, these values are good. Laminar case, above 10 to the 4th, less than 10 to the 9th. Turbulent case, above 10 to the 9th, less than 10 to the 3rd, 10 to the 13th for the Rayleigh number. There's also an overall expression that encompasses pretty much all the Rayleigh numbers, whether it's laminar or turbulent, and given by this bigger, kind of longer, more complicated expression here. So again, as we saw in the forced convection cases, there's a lot of times with these empirical relationships, more than one equation to use, and whichever one you want to use is pretty much up to you. They should all give you relatively the same numbers. So it shouldn't really matter whether you want to use this one or say that one. Obviously, if it's laminar or turbulent, you need to use the right one, but it's up to you whether you want to use kind of the simple version or the more complicated version. Another interesting case happens with horizontal plates. So the vertical plate was nice and easy. I had this boundary layer that just went up the side of it. The horizontal plate is kind of interesting if you think about what happens, because if I have this plate here that's really hot, that's going to heat up the air around it. The air around it, when it gets heated up, has lower density and therefore wants to rise. So off the top of the plate, I'll just have air rising off the top, but off the bottom, air is going to want to rise, but there's a plate in the way. So to rise, what the air has to do is actually go around the plate. So that ends up having different heat transfer coefficients from the top and the bottom. You have different mechanisms going on. So for a hot plate, upper surface, I have the Nusselt number 0.54, Rayleigh number to the 1/4 power. That's for Rayleigh numbers between 10 to the 4th and 10 to the 7th. Or if I'm between 10 to the 7th and 10 to the 11th, different expression, 0.15, Rayleigh number to the 1/3. That's for the top surface of a hot plate. Lower surface, Nusselt number is 0.52, Rayleigh number to the 1/5. Again, range of Rayleigh numbers where it's valid. So that example was for a hot plate. If this was a cold plate, cooling things down, then the exact opposite would happen. So this whole thing would be basically upside down. On a cold plate, the air would be moving down off the bottom, and then on the top would want to move around and down. So these equations work there as well. Just have to make sure that if I'm on a cold plate, this is the lower surface, and a cold plate, this is the upper surface. So make sure you use the right equation for the right surface based on top, bottom, hot or cold, what's happening, whether it's just moving straight off or whether it has to go around. So basically these equations, if it's just moving straight off, this equation, bottom equation, if it has to go around. Next up is cylinders. So long horizontal cylinders, again, have the equation of the form C times Rayleigh number to the n power. Again, here, Rayleigh number based on diameter. And then again, like the cylinder case for the forced convection, there's a lot of different values of Reynolds number with a lot of different values for C and N. So again, just find the Rayleigh number, whatever the Rayleigh number is, find the right range, whatever that range is, find the right value of C and N, plug it in there, there's your Nusselt number. Then again, you can find your H, because H, or Nusselt number is H times D over K. So that, again, is one option. There's also a second, more complicated equation, useful for many Rayleigh numbers, so you don't have to worry about which range you're in, but it's a more complicated equation. Again, up to you which one you want to use. They should both give you relatively close values for the Nusselt number. And then finally, spheres, free convection for spheres. This is the most recommended equation. Again, the book probably has other ones, but that is the one that's most useful, at least in my opinion. Again, valid for certain values of Rayleigh number and Prandtl number. So those are all the equations to use for the free convection case. Again, just want to make sure that you have the right equation based on geometry and based on flow conditions, in this case, namely the Rayleigh number. All these results summarized, table 9.3, pages 433 to 434 on the textbook. So that's a good place to look as a nice summary, which one to use when. So next up, a few examples. So the 0.5 meter square vertical plate maintained at 65 degrees Celsius, exposed to atmospheric air at 15 degrees Celsius. Want to know what the heat loss is due to free convection. So obviously, first thing to do, again, procedure-wise, same as the forced convection case. I want to find the film temperature. From the film temperature, I want to find, in this case, the Rayleigh number based on the Grashof number. So forced convection case, it was the Reynolds number, but now this case is a Rayleigh number. Once I get that Rayleigh number, want to find the right value of the Nusselt equation to use. Then from that, I can find H and I can find Q. So first thing, the film temperature. Temperatures in this case, I already forgot, they were 65 degrees and 15 degrees. So average of those is 40 degrees. So air at 40 degrees from table 8.4 has a kinematic viscosity of 1.76 times 10 to the negative 5. That's in meters squared per second. K value 0.0275. That's watts per meters degree Celsius. And Prandtl number dimensional is 0.705. Then for my volume coefficient of expansion, any value for liquids will be given in the table, but any value for gases are not, and that's because you can assume gases are ideal gases. For an ideal gas, the volume coefficient of expansion is simply 1 over the temperature. Make sure that's in Kelvin. So 40 degrees, 313 degrees Kelvin gives me a volume coefficient of expansion of 0.00319 per Kelvin. Then Grashof number, G beta T wall minus infinity, length cubed over nu squared. So gravity 9.81, beta value 0.00319, temperature difference 65 minus 15. The length of my plate was 0.5 meters, cube that. Then this kinematic viscosity of 1.76 times 10 to the negative 5 square that gives me a Grashof number of 6.3 times 10 to the 8. This is less than 10 to the 9th, so this is laminar. Technically, this times the Prandtl number, which is less than 1, so that's going to be a smaller number, so still less than 10 to the 9th, so this is laminar. So for the laminar case, I need to evaluate this weird function g for the Prandtl number, and so just sticking the Prandtl number of 0.705 into this big long equation gives me that function g of 0.5. Then I can use my Nusselt number, 4/3 Grashof number over 4 to the 1/4 power times this function g. So 4/3, 6.31 10 to the 8 divided by 4, all to the 1/4 power times this function, which was 0.5, gives me a Nusselt number of 74.7. Then I can find my h value, Nusselt number times k over L. So 74.7, k value 0.0275, length was 0.5 meters, gives me an h value of 4.1 watts per meter squared degree Celsius. And finally Q, standard equation, HA T wall minus T infinity, 4.1 H, area 0.5 times 0.5 meters, and then temperature difference of 50 degrees, gives me 51 watts for the heat loss from this plate. Second example, again, have a 1 meter square, well, slightly bigger, 1 meter square vertical plate, still vertical. This guy's maintained at 49 degrees, exposed to room temperature at 21 degrees. Again, want to find the heat loss by this plate. So in this case, again, want to find my Grashof number. I feel like I'm missing a slide. So I have 9.8 for the Grashof number, beta, again, 1 over the film temperature in Kelvin. So this guy has a temperature of 49 and air is at 21. So film temperature there would be 35 degrees. So 35 degrees Celsius. In Kelvin, that's 308. So 1 over 308 would give you 0.0325. This temperature difference, the length of my plate, 1 meter. The Prandtl number, so air at 35 degrees Celsius would have a Prandtl number of 0.706. That'd be from that same table, A4. Kinematic viscosity, again at 35 degrees Celsius, from that same table, A4 would be 1.6 times 10 to the negative 5. Gives me a Grashof number times the Prandtl number of 2.46 times 10 to the 9th. This is bigger than 10 to the 9th, so this is the turbulent case. So slide 11, I can go back to that, and in the turbulent case, I have the Nusselt number C times Rayleigh number to the some power. C is 0.1, power is 1/3. So 0.1 times 2.46 times 10 to the 9th to the 1/3 power gives me a Nusselt number of 135. H value, K over L, so 0.0268. Again, that's the K value for air at 35 degrees Celsius from table A4. Length of 1 meter, Nusselt number of 135. Gives me an H value of 3.62 watts per meter squared degrees Celsius. And Q value, 3.62, 1 meter squared, 49 minus 21, grand total of 101 watts. So that is the first way we could do this, using that simple equation. So simple equation, I mean Nusselt number, C times Rayleigh number to some power. There's also that second alternative equation. So we use that guy, nu to the 1/2, 0.825 plus 0.387, Rayleigh number to 1/6 power, plus 1 over 0.492 over Prandtl number to the 9/16 power, whole thing to the 8 over 27 power. Plug in all those numbers, gives me a Nusselt number of 142. Previous equation gave me a Nusselt number of 135, so slightly less. In the previous case, slightly bigger in this case. If I plug that into my heat transfer equation, gives me a Q of 107, which again, slightly bigger than the previous case of 101, but close enough. So either one you want to use is fine. Then last case, or last example, I have a 10 centimeter length of platinum wire, 0.4 millimeters in diameter, placed horizontally in a container of water at 38 degrees Celsius. It's electrically heated so that the surface temperature is maintained at 93 degrees, and want to find the heat lost by this guy. So basically a cylinder, horizontal cylinder. So film temperature, 93 plus 38 divided by 2 gives me 65.5 degrees Celsius. And then table A6 for water, want to find all of its properties. So density of 980 kilograms per cubic meter, heat capacity 4,188 joules per kilogram Kelvin, viscosity 4.3 times 10 to the negative fourth kilograms per meter seconds, thermal conductivity 0.659 watts per meter degree Celsius, Prandtl number is 2.73, dimensionless, and then beta value 5.58 times 10 to the negative 4 inverse kelvins. So again, that guy, because it's a liquid, find in the table. And then I can find my Rayleigh number, GR, PR. There's actually a secondary way to calculate it. So we had one equation for GR previously. This combination, GR, PR, which is the Rayleigh number, can also be found using this equation. So G times beta, density squared, heat capacity or over viscosity, thermal conductivity, length, in this case diameter, cubed, and delta T. So G is 9.81, beta 5.58 times 10 to the negative 4, density 980, square that, CP 4188, viscosity 4.3 times 10 to the negative 4, and thermal conductivity 0.659. Then diameter was 0.4 millimeters, so 0.0004 cubed. And then temperature difference 93 minus 38 gives me a Rayleigh number of 273. So 273, again, I have two options. I can either use a simple equation, which was C Rayleigh number to some power n, and these values of C and n depend on the Rayleigh number. For 273, C is 0.85, n is 0.188. You can see that from wherever the slide is, this guy here. So 288, I'm kind of in this range. So from 100 to 10,000, so C 0.85 and 0.188. Or I can use this equation down here. So again, you're going to do that both ways. So the first way, use simple equation, I get a Nusselt number of 0.244. Second way, using that big long equation, get a Nusselt number of 2.22. Again, fairly close values. Then using my H value, or finding H, K over D times Nusselt number, standard equation for heat loss, HA T wall minus T infinity. Area in this case is pi D times L, outer surface area of the sphere. That's going to give me either 27.8 from the first one, the simple equation, or 25.3 from this longer, more complicated equation. Again, fairly close to each other. Doesn't matter which one you use. So that is free convection over a multitude of geometries and conditions. So that is it for today.